Very good. So, I'm sorry for being off the air so long, and I'd like to give a make-up class maybe even on Friday, but we'll discuss that at the end of this lecture. Now, before I start on what I want to discuss today, let me just make a little comment on something I did last time and had a very useful question at the end of it. So, last time, among various things, we basically completed a quick discussion of supersymmetry, and one of the things we concluded was that the kinetic term for gauge theory, for a non-abelian gauge theory, that the kinetic term was the trace here and plus complex conjugate with some coefficient, and W was the gauge superfield field strength superfield, which is 3 T's on V. Now the question that I was asked after the class was that, okay, I argued that this reproduces minus a quarter trace F mu, and the question I was asked was, can we reproduce the other possible term of this dimension, which is theta trace F mu dual, where F, so this is the question, where F dual is a half epsilon mu beta. So this is the question, and the answer is actually very nice, and so I should have said it in fact while doing this. And the answer is to reproduce this, just put in a complex coupling. You know that in certain conventions we would like to put a 1 by g squared here, that would give us a 1 by 4 g squared here, and that's a natural convention for gauge fields in which the field strength itself doesn't depend on g. And all we need to do is replace 1 by g squared by something like tau, which is let's say theta. So we would replace 1 by g squared probably by I tau in that case. I don't know, I'm not going to do factors over there, we'll have to figure those out. But logically something like this. Okay, so you see that this contains 1 by g squared, but also an imaginary term. And what happens now is that we put in this tau in here, and then when we say plus complex conjugate, we have tau bar times the d2 theta dagger term. Okay, so the whole thing is perfectly real. Okay. But what happens then is that if you break up all the terms into their real and imaginary parts properly, you find that 1 by g squared comes with this interaction, and theta with some 2 pi or whatever it is comes with this. Okay. So therefore you can actually reproduce both FF and FF tilde, the so-called theta term in super QCD. And this actually teaches us a very important lesson, which is that in supersymmetry, couplings are naturally complex. Because that lesson in this case comes from the fact that if we just decided to complexify the coupling constant without having any motivation for it, first of all, the prescription of writing an F term is always write the term and add its complex conjugate. So the Lagrangian is real. Nobody is afraid that the Lagrangian will be complex. Okay. But what you get at the end of doing this is both the term you want and a new term which actually you also want. Okay, and which plays an important or potentially important role in QCD, the theta term. Okay, so
but in QCD it's like we do not have any FF tilde term in the Lagrangian.
We do. Sometimes we don't put it, but it's a possible term. It's a renormalizable coupling. It has physical effects. So it is part of it. Well, in some variants of QCD, it might be possible to rotate it away, but in general, it's there. Okay. So that's for last time. And are there any questions? Otherwise, I'll start on the MSSM. Now, I realized that I had taken a lot for granted when I embarked on this course, and one of the things that I thought was that people knew all about supersymmetry, and the other thing I thought was people knew all about why we are doing supersymmetry. And of course, I know that most people here do know both of these things, but it doesn't hurt to remind ourselves of some motivations. And so the first thing I want to discuss here, but only for a short time, is motivations to think of supersymmetry at LHC, because after all, this course is supposedly LHC for string theorists, and I have to even explain to you why such a the course with such a title is about supersymmetry at all. Now, there are two things that I just want to say here in brief, but I very strongly recommend to you Weinberg's textbook, volume 3, which is on supersymmetry, his quantum field theory textbook in 3 volumes. Volume 3, chapter 28, has 2 sections, I think 28.3 and 28.4 possibly, which have a nice sort of set of motivations as well as physical arguments about why supersymmetry should be there, what problems it solves, what new problems it raises, and so on. In fact, I find this whole chapter rather profound, and if I had had more time to read it in depth, I might go into more right now. But if not, I'll probably get back to this subject next time. So briefly, the motivations are as follows. One is cancellation. Okay, both motivations that I'll discuss here come from the assumption that the standard model is somehow part of a larger theory with a higher energy scale. Okay, so both motivations come from unification. Now, if the theory is part of some structure with a higher fundamental energy scale that's possibly close to the Planck scale 10 to the 19 GeV, although it might be 2 or 3 orders of magnitude lower than that, then certain consequences flow, because we assume that there's a unified theory with a single gauge group at that higher scale, and as we evolve the theory down to lower energies, the gauge group splits into our familiar S3 cross S2 cross U1, which is certainly the direct gauge group at low enough energies. Now, this leads to a puzzle, because in this high scale theory, there will be certain high mass particles which are supposed to decouple from the theory, so that the theory is left with only the fermions and gauge bosons and Higgs fields that we know and love. And what will happen is that these higher mass fields will unreasonably influence the low mass physics in the following way. Imagine a very heavy scalar. Let's call it S, okay, coupled to the Higgs, which we'll call H. Then we have the following one loop diagram, where this is an H and this is an S. We'll assume that they have H squared S squared coupling, which is a renormalizable quartic coupling, okay. And if you evaluate this diagram, you'll find that the loop part of it is this, where capital M is the mass of this S. And you're supposed to imagine that this capital M is a very heavy scale, like 10 to the 17 GeV. Okay? And if you evaluate this thing in the usual ways, you'll find that there is a term proportional to M squared times some logarithmic, or actually more precisely, if you evaluate this with the cutoff, you'll find that there's a term proportional to lambda squared, which is the cutoff, and the natural value of lambda will be this m when you renormalize this theory. So this is a problem because it means that there's a contribution at one loop to the Higgs mass which is so large that it's possibly 15 orders of magnitude more than the actual Higgs mass that we expect. Okay? We expect the Higgs mass to be in the range of 100 GeV or in that ballpark, and this is going to give a contribution which is 15 orders of magnitude. That's a huge amount, larger than that. And of course, when we renormalize the theory at one loop, we are free to subtract off that thing. What we have to do then is to subtract off 10 to the 15 or 10 to the 17 and then add back 10 to the 2, which is called the fine-tuning problem. You subtract off a huge number and then you add back a very small number to reproduce its mass. And this problem is cancelled or cured if the high-scale theory is supersymmetric. If the theory is supersymmetric, then S, that's heavy scalar, has a fermionic partner, because this heavy scalar will by assumption be part of a chiral superfield. There will be a fermionic partner, let's call it psi, and then there will be a coupling dictated by supersymmetry in which the Higgs, the same Higgs, will come in and go into a loop of psi and go out as Higgs. Psi will have the same mass as S, so again of mass m, and this integral will evaluate again to something of order lambda square, and therefore eventually after renormalization to order n square, which means this is another contribution of the same order as this. Now the remarkable thing which you can convince yourself by actually doing a calculation is that if these two fields are actually governed by exact supersymmetry, S and psi, that is if they are part of the same chiral multiplet, then numerically this answer and this answer are exactly the same up to a minus sign, and therefore with supersymmetry the quadratic terms add up to 0. Terms cancel exactly. That still leaves logarithmic divergences, but those are much softer, milder, and the fine-tuning problem is correspondingly mitigated. Okay. In fact, if you formulate this discussion in superfield language and just say that the Higgs superfield has a loop of some other superfield and use superspace Feynman diagrams, then manifestly you never get these terms at all. They cancel internally because of supersymmetry. Okay. So what supersymmetry typically does is to take a bosonic contribution to a diagram, a fermionic contribution to the same process, and cancel out some leading divergent part of them. Okay. It's well known, of course, from the very simplest thing that supersymmetry does, which is the vacuum energy in a supersymmetric theory. If you just regularize the theory in a box and add up the vacuum energy contribution from bosons and fermions, it cancels, and this is a generalization of that phenomenon. Okay. So that's motivation 1. Motivation 2 is again related to unification, but it's based on a rather striking miracle, which of course has been well known for at least a couple of decades. So this is the Georgi-Quinn-Weinberg calculation. Now, not being an expert on this, I can't tell you how robust this calculation is as a support of supersymmetry. It seems to support certainly the MSSM or something very close to the MSSM. And what it does is that it says with the field content and couplings of MSSM, which we are going to list in a few minutes, the RG evolution of coupling constants up to a high scale looks like, so this is the energy, here's the coupling constants, G, let's say G squared, where this G can be Gy, G2 or G3 in my notation, the coupling constant of the hypercharge U1 or of SU2 or of SU3, and you you find the following picture. But this is some energy scale that could be around 10 to the 17 GeV. The point here is that this is G3 square, this is G2 square, and this is Gy square. This being U1 is asymptotically increasing while the other two are asymptotically free, being non-abelian, they decrease. And as you can well imagine, three such curves have very little chance indeed of meeting at a point. Okay. And if you do the same calculation in the standard model without supersymmetry, they really do not meet at a point. Okay. Each pair of these three curves meets at a different point. But with supersymmetry to a very, very high degree of accuracy, they do meet at a point. As I said, you could ask lots of questions like how much accuracy, what assumptions go into it, and I'm not going to go into that, but I'll refer you to Weinberg's book, chapter 28, for a discussion on this G2W calculation. Yes.
This is for MSSM or supersymmetry?
MSSM.
The first example,
Sorry.
only introducing supersymmetry.
Yeah, so the first motivation is very generic for supersymmetry, but this, for example, can be destroyed by just tampering with the Higgs content of the MSSM. I'll tell you just now in a moment what the Higgs content is, and I'll make the claim that if you change that, this is again discussed by Weinberg, if you change all that, if you fiddle with various parameters, the Weinberg angle and so on, then you won't get this. So this is in fact more than a support of supersymmetry, seems to be a support of the MSSM itself. Okay. Now it's a very interesting sociological fact. For many years, this was touted as one of the great successes of supersymmetry, but in the last 6 or 7 years, there are alternative scenarios like large extra dimensions and so on, in which we are supposed to believe that this is a total coincidence, has nothing to do with the real world. Okay, so it's important when we start thinking about LHC that experiment is going to hopefully resolve for us this question that here's a beautiful theoretical result, meeting of three curves at a particular point with enormous consequences for physics, because it would say that physics is truly unified at this energy scale. Okay. Is it a coincidence or is this a pointer to something very, very deep about nature? We don't know the answer. But the MSSM is based on the assumption that the answer is yes. And to the extent I can understand, all other scenarios not involving supersymmetry, including large extra dimensions, brane worlds and so on, are based on the assumption that the answer is no, namely this calculation means nothing at all. I know certainly as of 3 or 4 years ago when Edwin gave some lectures on particle physics at a Princeton summer school, he certainly took the point of view that he believed this to be a very strong result, and his entire belief on what we should expect at high scale to come out of high scale physics is based on this. But it's a very personal opinion. Okay, good. Okay. So with these, are there any questions or comments? Okay. So with these motivations, let us finally start on what's called the minimal supersymmetric standard model. And in keeping with the somewhat phenomenologically challenged nature of this course, or at least of myself, I'll go into this a little bit slowly and try to check out what are the basic properties rather than dazzle you with the Lagrange's written over several hundred.
The thing that you mentioned here, like the measure of all the coupling constants.
Yes.
Now, is it so that they have the same case theory or this? Like, how is it?
Yeah, so the point is that the merger is consistent with the assumption that at this scale, a single unified gauge group such as SO10 or something takes over. Okay. Depending on what actually takes over, the evolution beyond this would be different, but it's not possible for any one gauge group to take over here unless this condition is met. So it's a sufficient but not necessary condition for unification. Okay. Or if you work it backwards and imagine that there is a unified theory there, then without knowing much about that theory, except that this is the scale at which that gauge group is broken, then it follows that 3 lines, if it's broken precisely into SU3 cross SU2 cross U1, then 3 lines emanate like this. Maybe I should say, at the risk of again delaying my actual lecture by a minute, that there are enormously many assumptions, and people sometimes get very annoyed with this bland kind of reasoning, because this is us, this is the unified scale. There are 15 orders of magnitude in between, and in order to produce these lines, we are assuming that nothing happens in between, which is called the desert scenario, that there are no new particles or interactions with any characteristic energy scale in between here and there. Okay, it's considered, wildly, not just optimistic, but wildly sort of, I don't know what the word is, extrapolative argument. Okay, so this is, I think, I wanted to mention this particularly, this picture and this calculation, and I do urge you to go look at Weinberg's very carefully. He described this calculation in section 28.3 of all, modestly not calling it Jacqueline Weinberg, but whatever, it's there. And the thing is, on the one hand, the agreement is, the coincidence is stunning. On the other hand, the assumptions are also stunning. So,
So you have heard the statement that the scalars in the MSSM appear in complete SU5 multiples, and therefore dropping the scalars would not change this meeting.
Okay.
You know that's.
No, I haven't gone into this, though I do plan to, but I haven't yet gone into it in detail. But my impression was that the 2 Higgs doublet structure of MSSM is crucial for this to work. So probably by scalars they are referring to the quarks and leptons or something. I've heard this statement too, but I will talk about it more when I'm more comfortable. Okay, so what do we want to do with the how do we want to invent the MSSM? Well, we've done the standard model, and now we have to ask the following question. Either some 2 particles in the standard model are superpartners of each other, or we have to introduce a new superpartner for every particle that's in the standard model. These are the only 2 possibilities, and it's a very quick check of quantum numbers will show you that no 2 particles of the standard model can be superpartners of each other. Forgetting even the fact that superpartners should have the same mass, which we've already seen, I'm anticipating, of course, that the supersymmetry we are introducing here will be broken. It's certainly broken in the world we live in. So here there should be 2 different scales. The scale below a TeV, where the supersymmetry is certainly broken, and the scale around the TeV or above, where we hope supersymmetry will be restored, and that's typically will determine the masses of the particles we are going to see. Okay. So even assuming that mass splittings are possible, and I'll be discussing mass splittings later on, it still remains true that no 2 particles of the standard model can be superpartners of each other, just based on quantum numbers. Okay. For example, the quarks are triplets of sq3, and there are no scalar fields in the standard model which are triplets of sq3. Okay, so there have to be some new particles which are the superpartners of quarks. Same for leptons, same for Higgs, same for the gauge. Okay, they're all got some properties which are not met by any other particles in the standard model, and so we have to introduce new ones. So let's do it as follows. Let's start with so now this leads to the new terminology which Dries, Goodwille and Roy sometimes use, but you have to be a little careful with it. Particles versus sparticles. So these are in the standard model. Everything that's in the standard model we call particles, and everything that's new and has to be postulated in order to have supersymmetry are called sparticles, and they are not in the standard model. Okay. But of course we will be able to figure out these particles in one go if to every particle we associate a superfield, and that superfield will contain the particle as well as this particle, and it will sort of determine what this particle can do. So, therefore, the logical way to proceed is to list every particle in the standard model and find out what its corresponding superfield is. Okay, so we start with the fermions, and for these, we'll, for example, this is all notation and it's extremely obvious, but I have to do it. I've tried to simplify it considerably from the DGR book. Okay, so here's a electron doublet. In the standard model, there's a doublet called electron, neutrino, and electron. Those are two fermions in an SU2 doublet of the SU2 gauge group of SU3 cross SU2 cross U1 and with some hypercharge assignments. And what I've done here is to just write superfields, chiral superfields, in the same kind of doublet. So when I write LE is a function of x, theta and theta dagger. This is only I'll do it only once, after that you'll have to get used to this. Okay. It's going to have a starting term which is a scalar, a complex scalar, and then it's going to have root 2 theta times a left-handed fermion, and because this is LE, the fermion here is going to be E left. Okay, and then it will have an auxiliary field which we never need to worry about because that will get eliminated by equations of motion. It's not a new particle. The new particle is here, and this particle we will call E tilde L, and it will be called the left selectron. Okay. Now you have to be very, very careful with your terminology. The left selectron is not left-handed in any sense of the word, because after all it's a scalar particle and it can't be left-handed or right-handed, it's just scalar. Okay. What makes it the left selectron is that it's the super partner in the same chiral superfield of the left electron. Okay. So maybe a more appropriate notation would be S of in brackets left electron. Okay, just call it the left selectron. Fine. Now, obviously, the same procedure works for the neutrino, so we'll have a left neutrino. Okay, but this is only the left-handed SU2 doublet. Okay, now as you can see, steadily in this course, more and more indices are going to be suppressed, and I emphasize again and again, you must know how to put those indices back. Okay, for example, you have to realize that this has an index which makes it the lower component of a doublet. That index is possessed by this and this. On the other hand, this has also an index which makes it a two-component fermion, while this is a scalar, so it doesn't have any such index. The two-component fermion index of this contracts with theta. Okay, so you have to keep doing these exercises. So much for the left-handed doublet. What else do we have in the first generation of leptons? We have a right-handed singlet. Okay. Now, last time we went through this, I think, in considerable detail, and we realized that a right-handed fermion cannot be part of a chiral superfield. It has to be part of an anti-chiral superfield. Okay. Necessarily, a chiral superfield must contain only left-handed fermions because theta is undotted, and undotted means left chiral. Okay. Therefore, we have to introduce the left-handed positron and put that in a chiral superfield, and I'll give that the name E bar 1. And I'll be using this notation consistently from now on, and I think it's quite a good one. Bar means antiparticle, but doesn't represent complex conjugation, which I'll reserve for dagger or star. Dagger on fermion, star on boson. Okay. In other words, E bar 1 means the anti-electron. Okay. Since there is no complex conjugation, this is a chiral superfield. Okay. There is no superfield called E. The anti-chiral superfield for this is called E bar dagger. Okay, and so E bar contains in it, in its expansion, a term which you can call E bar tilde L, which is the left positron. Okay, and then here it contains the left positron. So that's E bar. Okay. Finally, these ones refer to the first generation. So without any further work, you can extend this to L2 E bar 2, L3 E bar 3, where L2 is the muon neutrino and muon superfield, left-handed, and then the left-handed anti-muon, and then the same for nu tau and tau, and the left-handed anti-tau. So that takes care of all the superfields for the electrons. And in this course, for this in this period, we are not discussing right-handed neutrinos because that's a whole separate discussion. So we are pretending that we are in the old MSSM in which neutrinos were exactly massless. I must say I don't have enough experience to know if it's a good thing to pretend that neutrinos are exactly massless and work with neutrino masses later, or it's just a historical thing that while these books were being written, neutrinos were sort of started out massless and ended up massive by the time that they went to press. I really don't know that, but my inexperience means that I'm going to sort of follow this because at least I feel some confidence in the formulae as they're expressed here. Okay. Now, the same thing works for quarks perfectly, except that now, for every left-handed doublet, so Q1 will be the left-handed doublet QU and QD. QU will be the chiral superfield, whose second component is the up quark, left-handed up quark. Its first component, therefore, is the left up squark. Tilde is used for particles most generally. So if some symbol has been used for like an electron, then the same symbol with tilde will be this electron. So U tilde left. Again, remembering that left is not a property of this thing, it's a scalar, it's just the left, this is the partner of U left. Then root 2 theta, U left, and auxiliary fields. Okay. However, now we have to introduce two SU2 singlet chiral superfields called U bar and D bar, both with ones. Okay, so these represent the up antiquark left-handed and the down antiquark left-handed. Okay, both are necessarily there, and then extending one, the index 1 to 2 and 3, we get the charms there, top and bottom. Okay, so that takes care of all the fermions in the standard model. Are there any questions? In particular, we see that every one of them has a scalar field, complex scalar field as its superpartner, and that wherever there are left and right-handed fermions, then each one has a different scalar superfield as its partner. Okay? Good. You might have asked why these fermions were all in chiral multiplex and not, for example, in vector multiplex. That's because in vector multiplex, the fermions are necessarily in the adjoint representation, while none of these is in the adjoint representation. Okay, these are all complex representations. In particular, the adjoint is a real representation. So the only choice we had was to put them in chiral multiplex. So the summary of this is one chiral multiplet for every electron and quark. Okay. Now come to gauge fields. It's extremely simple, painfully so. So we have the hypercharged gauge field, 3 W's. These are not the physical W's yet. We know that they come out from these, and one of these combines with this to form the photon and the Z. And then we have gluon fields G mu A. And I'm not being very particular about this notation, but you recognize that here A must go from 1 to 3 and here from 1 to 8. Okay, so these already exist. So we embed them into vector multiplets, which are V. Now you can give V a kind of subscript or superscript to indicate that it belongs to the P gauge boson, and that's contained in it, or you can just give it the superscript Y, which I like for hypercharge. Then V A superscript 2 for SU2, and then V A 3 for SU3, and here A goes from 1 to 3, and here A goes from 1 to 8. Okay, so all we've done is to take all the existing vector particles and put them into vector multiplex, whose middle term, theta sigma mu theta dagger, will contain precisely these gauge fields. So that takes care of the vector fields. And finally, the Higgs. Now in the standard model, there is a single Higgs doublet. So you would expect that in the supersymmetric case, we just extend this to a Higgs doublet superfield with the Higgs doublet as its first component. That turns out to be wrong, or actually inadequate, for a variety of interesting reasons, and so I'll show you that now. First of all, let's recall the doesn't work. When I say doesn't work, it turns out that one Higgs doublet is not enough, and in the MSSM you must have at least two Higgs doublets. Okay. I say at least because, of course, you can always go to less and less minimal or more and more non-minimal things, even in the standard model. The minimum in the standard model is 1, and in the MSSM is 2. So let's see the reason. So let's recall that the standard model Yukawa couplings were as follows. I'll just write the ones involving quarks. If you remember, I had introduced this slightly weird notation. Now we'll understand why. And the first line are the terms which give masses to the down quarks when phi gets a rev, and the second line will give masses to the up quarks. I had written only these two terms when I reviewed the standard model. They all involve right-handed quarks, and these are the other two terms that are their complex conjugates. They involve left-handed quarks. And while you might be inclined to take these f's to be real, I told you that in supersymmetry they are naturally complex, so we'll just let them be complex. But clearly this plus this is real, and this plus this is real. So far everything is okay. Now, the thing is, the Higgs field managed to play a double role. It managed to give a mass to the down quark as well as to the up quark. And the reason is, if you like, that what gives a mass term for the left up quark is phi, but what gives a mass for the left down quark is phi star, the complex conjugate. Okay. If you really work out all these indices properly, this phi star might actually be a phi c, which is complex conjugate and some epsilon symbol multiplied in. I'm not worrying too much about that. The important thing is that if we generalize to superfields, then we've already seen that QL goes to a superfield Q, let's say 1, and D bar L goes to the superfield that I've called D bar 1. Now we seem to be, and U bar L goes to a superfield that I've called U bar 1, and all of these are chiral superfields. None of them is anti-chiral. Okay, and we know that the interactions of this sort come from F-term couplings among chiral superfields, which can't involve the anti-chiral part. Okay, so if I want, for example, to reproduce this term, then phi must be a chiral superfield. But if I want to reproduce this term, then phi star must be a chiral superfield, and this is incompatible. Okay, so what I do is I choose phi to be extended to a superfield H, which is chiral, and I call it H2. Does anyone remember what was the hypercharge of phi? We chose it in the first. to be plus 1. Thank you. So therefore H2 will have y equals plus 1. It's called H2 for some reason. Okay, and introduce another Higgs doublet superfield. H1 with y equals minus 1. Okay, then what we'll do is we won't have this coupling. In fact, phi, this field H2 will not appear here at all. Instead, H1 will appear here. Okay, so instead of phi star where this is phi, it's another phi appearing here. Totally independent field. And so therefore, our complete list of Yukawa couplings turns into, I'm only writing the quad case, you can easily read off the electron case. Maybe I have it, I don't know. So let's write it first and then see how it works. Minus f star d integral d to theta dagger. Maybe I'll prefer to write the d to theta. Q1 H1 d bar 1 plus Cc and minus f of u integral d to theta Q1 H2 m bar. So let's see if this makes sense. Q1 H2 u bar 1 reproduces this. Okay, H2 is the one whose scalar component is identified with the standard model Higgs, and Q1 u bar 1 contain these quarks respectively. So that is this. Cc is of course that term. Okay. On the other hand, here Q1 contains this, d bar 1 contains this, and H1 replaces phi star. Okay, and if you remember, here the hypercharge is worked out because we had to use the hypercharge assignments for quarks, for all the various quarks, and then plus 1 for phi and minus 1 for phi star. So if you accepted this in my first or second lecture, then you agreed that the hypercharges were right. And now I've got an H2 with the hypercharge plus 1 and I'm putting it in here, so it works. And here I'm using an H1 with hypercharge minus 1, so it also works. So all the various charges that need to be conserved are conserved. And of course, you have to remember that this quark is a doublet, this phi is a doublet, and when I multiply this doublet with this doublet, I get an SU2 singlet. This is already an SU2 singlet, the whole term is an SU2 singlet.
Actually, yes, this is very embarrassing, but can you tell me what the Q and D stand for, please?
Here?
Yeah, little q, what is little q bar and
this one and this one?
Yes.
So this is the left-handed quark, it's actual fermion with the fermion index. Okay, so it's the left-handed quark doublet. So the quark doublet Q left is actually the doublet U left, D left. Okay, that's really all you need to know. And D bar left is what it appears to be.
It's D bar left.
Okay, and then phi is also a doublet. And basically, I really should have called this C rather than star. So what happens, if you remember in the standard model, is that this guy gets its wave in the lower component, because after the Higgs mechanism, this two-component object has its upper component charged plus and the lower component neutral. It's the neutral component which can get a wave, otherwise charge conservation will be broken by the vacuum. The lower component wave pulls out from here, Have I done something wrong? Or was it the upper component? Sorry. Upper component. No, lower component. This should be pulling out a UL from here. Probably this contraction is this is an SU2 doublet, this is an SU2 doublet. So there's a dot which is done by an epsilon. Okay. So if you do it that way, then you find that the lower component wave from here pulls out U left from here, and so we get wave V times U left, U bar left, which is the correct mass term. Okay. And in this one, on the contrary, because of this extra conjugate, it will pull out the other component, so the lower component from Q, so you will get D left, D bar left times the wave. However, the wave of this and this is the same numerically, it's the number V in terms of which we determined all the gauge boson masses. And now that doesn't have to be the case. So now yes.
All the bars are SU2 signals. Right?
All the bars are SU2 signals. All the bars are there because we had some right-handed singlets which we've converted to left-handed antiparticle singlets. But thank you for asking, and it's important to keep the notation sensible at all times. Okay. Now after the Higgs mechanism, which I am going to do in detail, but I am just anticipating things that we can very well guess. Because the Higgs mechanism will have to be worked out, I'll have to postulate the potential, write all the ordinary space terms, yes.
This kind of a coupling,
Yes.
what does it give apart from the Yukawa coupling?
It gives the masses to the quarks as well as the Yukawa couplings. But Yukawa couplings in the supersymmetric, this kind of coupling you're asking, right? Okay. So first of all, it gives masses to quarks, then it also gives masses to squarks. Okay, and then it gives couplings between quarks, squarks, Higgses, Higksinos in all possible ways which conserve fermion number. And to do that, you have to basically remember that a cubic superpotential, which is what this is, gives rise to a quartic ordinary potential from W prime mod square, as well as a Yukawa, ordinary Yukawa, with one of these being scalar and the other two being fermion. W double prime times psi sign. Okay, so you have to pull out all those possible terms from here. But remembering that the wave of this Higgs will be purely in its scalar quartics. Fermion term obviously doesn't have a wave. So at the level of wave, this can be, so this has to be expanded around its scalar. And then you'll see that it does everything you expect it to do in the standard model and more. The key point is though that first of all, the electric charge assignments of the Higgs, remember we can only know after doing the Higgs mechanism. Okay. After knowing how the Higgs mechanism will work in order to combine hypercharge and the three components of SU2 into the true electric charge. So it's going to be H2 plus and H2 0 is going to be H2, while H1 is going to be H1 0 and H1 minus. Okay. So remember, this is the guy which was more like the standard model Higgs, which took its wave in our conventions in the lower component. And this is like the conjugate of the standard model Higgs, which takes its wave in the upper component. And that's how they give different masses to the different quarks. The new thing though is that now the wave of the scale, take the scalar part, these are superfields, capital letters are the parallel superfields. The wave of the scalar part can be chosen, it will turn out, can be chosen real, very much like in the standard model, but we'll call it V2, while the wave of this guy can be chosen also real but independent, and we'll call it V1. So it actually looks pretty depressing that while we had one Higgs and one wave in the standard model, we have two Higgs and two independent waves in the MSSM. And this naturally suggests that we parameterize the ratio of these two waves, because after all we only need one of them to give a dimension. So we can think of some average value of V2 and V1 or the square root of their product as a dimensional quantity, and then define the ratio which is dimensionless to be tan of beta. And so beta is a very crucial parameter of the MSSM, which we'll hear whenever MSSM talks are given. Okay, so tan beta is the ratio of the waves of the two independent different Higgs.
So this breaks the superfield.
No, nothing. This doesn't break this. we haven't broken, we are actually working in a very ideal, first of all, we haven't written any interactions among these various superfields. Our philosophy is that, which I'll come to just in 5 minutes, is that there is an exactly supersymmetric MSSM, but it's obviously not right at the energies we are working at. But then we have to understand what to do with it to make it right, and it will turn out what we have to do is to add to it so-called soft supersymmetry breaking terms, and that will then be relatable directly to phenomenology. So we are working with a slightly more abstract kind of MSSM, which doesn't really exist in nature.
We are giving the vacuum expectation value only to the scalar.
Yeah, but that it turns out doesn't break supersymmetry for reasons which I will show you later, or if you really want, I can show you now. It's a rather beautiful fact that giving a wave to a scalar field doesn't break supersymmetry, and the reason, if you like, is this. Let's remember that. Okay, so here's the definition. I actually skipped a whole chapter called SUSY breaking, which should have been taught in the theoretical context before getting to this. But my motivation was that if I get bogged down in doing the theoretical properties of SUSY, I'll never finish, because that's the stuff I really like. And I really wanted to sort of see before my eyes what the MSSM looks like and what experimentally we see. But anyway, therefore, in fact, all of you will need to keep going back and covering these, understanding these things yourself. But anyway, let's do this quickly. So, the field content of a chiral superfield is phi, psi, and f. Okay. Now, after I make a supersymmetry transformation on phi, which is that epsilon q plus epsilon diagonal q diagonal on phi, I find a set of transformations on psi, on phi, psi, and f. And the question is, what do I get? Okay. So here, of course, I have to get epsilon psi. This is a kind of number-free notation. It's just what fields come out on the right. Okay. Delta psi has two terms. One varies into del mu phi. Maybe it's something like this. And another term varies into f. And notice that in 4 dimensions, both del mu phi and f have canonical dimension 2. So they can be added to each other. Right? And delta f varies into del mu psi. I may have got various details wrong, but I think very roughly this is right. Might be okay? Something like this. Now you see that in order to break supersymmetry, I must have something on the right side taking a non-zero wave. Okay? Because then when I have a configuration of phi, psi, and f, and I vary it, okay, its variation will not be zero, which means that configuration breaks supersymmetry. Okay, so SUSY breaking requires something on right side gets a wave. Now you see how few options there are. The fermion we certainly don't want to give a wave because it would destroy Lorentz invariance. Therefore, this also doesn't have a wave. Phi we don't mind giving a wave, but it better be a constant wave. Again for Lorentz invariance. Therefore, del mu phi doesn't have a wave. That leaves only our friend f, the auxiliary field, and in fact, it's a wave of f that breaks supersymmetry. Now, I haven't shown you that the Higgs mechanism, as it works out here, fails to develop a wave for f, but you will be able to check that it doesn't develop a wave for f, and therefore it doesn't break supersymmetry. Okay. Interestingly, if you repeat the same exercise with the vector multiplet, you will find that the only thing that can break supersymmetry is a wave for t. So we learn, this is again one of those beautiful facts in the early days, we learned that the auxiliary fields which look like a pain in the neck in the beginning, later we learn to like them, now we like them even more. First of all, we like them because they are the last terms of superfields, and so they are like invariant, supersymmetric invariant actions. But now we also see essentially for the same reasons that if they develop a wave, then supersymmetry is spontaneously broken. Okay. But this doesn't break supersymmetry.
Right. So the two Higgs will have some potential where they couple.
Yes.
And in particular, they'll be forced to be anti-parallel.
Yeah, that's the new term. Yeah, that's right. That's correct. Right. Okay. Now, one amusing fact is that we introduced two Higgs on grounds of wanting to give a mass to up and down quarks. Notice that if the world had only had leptons and if moreover the neutrino had been massless, then we'd have been in a luckier situation because we don't need to give a mass to the neutrino. In that case, in the lepton sector, only one Higgs is enough. Okay. So in fact, H1 or H2, I forget which, does the job of giving masses in the lepton sector. But in the quark sector, because both the quarks have a mass, that's the nuisance which makes us require H1 and H2. So it's, if you like, this is a phenomenological reason to have two Higgs. It's directly read off from an experimental fact, namely that quarks exist and are all massive. There are no massless quarks. Okay? But there's also a theoretical reason to have two Higgs, doublets in supersymmetry, which is worth noting. And as you might guess, this comes from anomalies. You see, the Higgs field is a scalar, so of course it doesn't have anything to do with anomalies, but the Higgs superfield contains a fermion. I didn't give you its name. Its name is Higgsino. Okay, and that Higgsino is a chiral fermion since it occurs in a chiral superfield, and it can very well contribute to an anomaly. And it turns out that with one Higgs doublet, you get a contribution to the anomaly, which is proportional to the hypercharge y cubed. So anomaly cancellation requires summation y of the hypercharges of the Higgsinos cubed to be 0. The Higgsinos have the same hypercharge as the Higgses, which is +1 for H2 and -1 for H1. So therefore, if I had only H2 or only H1, this would be non-zero, but it's 0 because of having both H1 and H2. Okay, one of which gives +1, the other gives -1 to the anomaly equation. So it seems that the minimum of two Higgs doublets is a theoretical requirement without which MSSM is inconsistent, and as Weinberg pointed out, it also follows that if we are going to increase the number of Higgs doublets, we must do so in pairs. If we add a new third Higgs doublet H3, then with a certain hypercharge, then we must also add an H4 with the opposite hypercharge because this equation has to equal. Good. Okay. So if this completes the spectrum. I think the last thing to say. Okay, so a couple of comments. So the Higgs, for example, H. Let's give it an index I. I hope you will automatically know what these indices are. In the case of Higgs, it's 1 and 2, but in the case of leptons and quarks, it's 1 to 3, which are the generations. Okay, you just have to. There's no point using different labels. It just makes it normal. So this starts with the conventional Higgs doublet field, but then it has a fermion, which has a name. It's called the Higgsino, and we've just seen that it contributes to this anomaly equation. So I didn't mention Higgsino explicitly. Similarly, the vector superfields, these have a lot of junk in the beginning, which goes away and so we know H. Okay. And then, as you know, they start with some theta, sigma, mu, theta, dagger, del, mu, A. So these are the, sorry, not del, A, mu, A. Okay. And then there's a cubic level term which is like theta, 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 dagger, lambda, A, dagger, plus CC. And then finally there's a quartic in theta term, which is the D term, which is an auxiliary field, so it's not a physical particle. Anything over here is not a physical particle because it's removable in Wessel-Wiener gauge. So that means that the gauge fields are supplemented by their super partners, which are called gauginos. So I didn't explicitly mention this earlier. Okay. The one thing important to realize about gauginos is that they don't contribute to anomalies, because like the gauge field, they are in adjoint representations which are real, which is real. Okay, and the gauginos have names depending on which gauge field it is. So if this was the B mu, the hypercharged gauge field, this would be the B no. If this was the W, this would be the V no, and if this was the gluon, then this would be the gluino. Okay, now the B no and V no, as we can guess, are not going to be physical particles, because the B and W are not physical particles. Only two of the three W's are physical. The third one combines with the B in order to make photon and Z. So the physical particles coming from these will be photino and xeno. Okay, so this is how it works. Except that even that won't be true, because there can be mixing between these things and the super partners of the Higgs-xenos. So Higgs-xenos and gauginos can mix, which is one of the most interesting things of the standard model, of the MSSM. Okay, good. Now we need to just write down the Lagrangian, and for this purpose now I'll assume no SUSY breaking and write down the Lagrangian for all the fields that we have. There are very few surprises, but it's worth writing it once. We'll be writing it in superspace. So what can L gauge be? It's going to be W. So W has a spinor index which is not going to be explicitly displayed, plus raise W2. I put this thing below to indicate matrix value. There you go. So these are matrix valued to 3 by 3 and these are matrix valued 2 by 2. Well, it doesn't matter. It could be in any representation of your choice, but you need to normalize it. Okay. But if you put them in the function, so there are 3 of these WAs, we dot them with 3 generators of SU2. If we take those in the fundamental, then it's a 2 by 2 matrix, then this is 3 by 3. We do the same thing. So this is clearly the kinetic term, which includes all F mu type things, plus complex conjugate. I'm not being very precise about coefficients. If you want the G's to occur inside, then you have to define the gauge field accordingly. If you want the G's to occur outside, then each of these terms should be divided by a corresponding Gy squared, G2 squared, and G3 squared. You can complexify them to get theta angles. Okay. Then there's L matter. This one, of course, is a D term, and it's basically the gauge invariant kinetic terms for all the superfields, for all the chiral superfields. So here's an example, and then I think you'll be able to write down the rest on your own. Li dagger, this is the lepton doublet superfield. Then it has to have an exponential of Gy, the hypercharged quantum, times V, Y, the hypercharged gauge superfield, times Y, the hypercharged value of that field. We've done this before, plus G tilde 2 times Li. So here's an example. Okay. So what this is saying is that the lepton doublet has hypercharge and it has SU2 quantum numbers. So we would like it to be gauge invariant under both, under local gauge transformations. That will be so if we put this exponential form for the vector superfield in the middle. And we don't have a V3 in this because the leptons don't have SU3 color. Okay. The definition of V2, we've already given this before, is twice G2 summation A V2 similar. This 2 is that 2 which is a slight mismatch between the supersymmetry and the ordinary gauge field conventions. So here's a term. What are the remaining terms? Well, for example, the left-handed positron has a term E bar I dagger. Remember, there is no superfield called EI, there is only E bar I and its dagger. This has only hypercharge. So this is the gauge invariant kinetic term. This Y is a number that needs to be evaluated every time we put it here. It's a particular number for the lepton doublet and a different number for the positron singlet and so on. All those numbers I've given you before. Then I'll write down one more and then I think we'll give up. Then just go on. QI dagger. Here you'll have everything. GY, VY, and Y plus V2 plus V3. Okay. And so on. So that takes care of all the gauge invariant kinetic terms for the superfields containing the ordinary fermions. That leaves the Higgs, but there are no surprises there. The Higgs, in fact, is rather symmetrical with this. If you just inspect this guy and replace L with Higgs, you're basically done. Okay, because Higgs has a hypercharge, Higgs has an SU2 quantum number, it doesn't have an SU3 quantum number. So L Higgs. This time I goes only over the two species of Higgs and it's HI dagger e to the GY VY Y plus V2. So that's that. Okay. Now comes the most interesting part, which is the superpotential. And here, let me first write what I claim is the answer, and then I'll try to justify it. First of all, I'll write a term that couples the two Higgs fields to each other, H1 dot H2. The dot is the SU2 invariant coupling, which means using an epsilon symbol. It's epsilon AB, this thing A, this thing B. Okay. Besides this, the other three terms that are present are no great surprise. We now introduce all the generations and allow for mixing.
It mu is a parameter.
Mu is a new parameter, yes.
So this is a quadratic term.
It's a quadratic term. It has to be a master. It is a master. Okay. Besides that, all the other terms are no surprise. I've already written them for you, except that I wrote them for you for a single fermion generation. And now, as we saw in the first two lectures, we need to allow arbitrary mixing in the Yukawa coupling among all the generations. So that's Fij. And then eventually we'll try to remove what we can of these Fijs, and whatever we can't remove turns into the CKM, Kabigo, Kobayashi, Masukawa matrix. And finally an FD, QI, H2. So this is the superpotential term, and now let's understand why we need this and why we only want this.
So what was quartic Higgs potential?
Yeah. So the quartic Higgs potential for the moment I am not putting in, because I'm going to do the Higgs mechanism sort of separately. So it's not the complete term. But even at this level, it's interesting to ask why we have this and what else is allowed. Now, it's clear that these three terms must be there. I've already shown you that they must be there. Okay? Because once you, if you have a coupling between three chiral superfields, then the ordinary space version is the scalar of one times the fermion of the other two. Okay, in all possible ways. You know this, I hope. People are looking very puzzled. Who was very puzzled? Yeah. I said the ordinary space, this is an interaction between three chiral superfields. The ordinary space version, if I integrate out d2 theta, is to take the scalar component of any one of these and the fermion component from the other two. and then do it in all possible ways. That gives you the ordinary space interaction from this. Okay, it's particularly simple when you have three distinct superfields. Okay, and that means, in particular, that we'll have the Higgs with a left-handed lepton doublet and the positron singlet, which is the correct term that gives the mass to the electron. And similarly, we'll have the Higgs here and the quark terms. Something is wrong. This should have been D, I suppose. Please stop me. Yeah. QI H1D. No. You're very obedient to class, I will say that. You believe this. This is FD QI H1. And this is FU QI H2. Okay. So I claim these are precisely the terms. If I reduce the Higgses to their scalars and these other things to their fermions, then they are the terms we already wrote before. And they are very much like the original standard model U covers, except for the fact that H1 is a new Higgs entirely and not just the star of the old one. We'll be into this. Okay. Now, first, let's comment on this mu term. I claim it's the most general gauge invariant mass term I can write. Okay. Because what else could I do? First of all, you know that I can't write gauge invariant mass terms involving the quarks. That was the whole point of the standard model. That the quarks are in different representations for left and right-handed. Therefore, there can't be any mass terms for the actual quarks. Therefore, by supersymmetry, there can't be any mass terms for the squarks. Okay. So, if the quarks have to get their masses through this Higgs mechanism, the squarks better get their masses through the same mechanism. And in fact, they'll get the same masses. Okay. Not so for the Higgs. For the Higgs, in principle, you were free to write an interaction. And in the standard model, there was an interaction, self-interaction among that one Higgs doublet. Phi dagger phi the whole square, phi dagger phi and phi dagger phi square. So that square we are postponing, but phi dagger phi equivalent I claim is this. Okay. The first thing you can see by inspection is that hypercharge of this is -1 and +1, so at least it's hypercharge neutral. Okay. H1 with H1 or H2 with H2 would have not been hypercharge neutral, besides which it would have been 0. Because this dot product is antisymmetric between these two fields because it involves an epsilon. H1 dot H2 is epsilon AB H1A H2B. And these are commuting objects because they are chiral superfields. Okay. For fermions, this dot product was okay even between the fermion and itself because the fermion components anti-commuted. Epsilon gave a second anti-commutation and so the whole thing was non-zero. But with bosons, you can't do that. So there isn't any H1 dot H1 and H2 dot H2. So notice vanish, and as I said, besides the fact that it vanishes, if for some reason it had not vanished, it would have failed to conserve hypercharge. That would have been another reason. So if you like, here's another way to see, it's more or less equivalent to one of the previous ways, but another way to see the necessity of two Higgs. You can't give a mass term to one Higgs if it's got a hypercharge. If it didn't have a hypercharge, you could have given it a mass term, but if it didn't have a hypercharge, you couldn't have done you couldn't have reproduced the standard model pattern of symmetry. Okay. Now, there are other terms we could think of. Okay. Now, one thing I want to stress for you, perhaps when we look at this, we instinctively think that this is a coupling only between a Higgs field and a quark and two quarks. Yeah.
So didn't you say that even if it didn't have a hypercharge, this thing, you couldn't have given it a mass term because this would have vanished?
Yeah.
Right.
Yeah. And so I've written that it's vanishing as the main reason.
Yes.
Because since it's vanishing, there isn't anything.
I just got confused. I thought you said if it didn't have a hypercharge, it could have given.
I see. If it didn't have a hypercharge and wasn't a doublet.
Okay. Yes.
Okay, so there are too many ifs. Right. A field in general, which isn't a doublet of SU2 and doesn't have a hypercharge, can have a mass term. It's not that supersymmetry makes it impossible, but it makes it pretty difficult when you have charges floating around and doublet representation floating around. This is the unique solution. Now, I was just pointing out that in this is really a cubic interaction between all superfields. Okay, so besides the fact that it gives you couplings between the Higgs and conventional quarks, it also gives you coupling between a Higgsino and a quark and a squark. You can pull out one scalar and two fermions in many different ways. Besides that, it also contributes to the ordinary potential, which means that an interaction, purely aquatic interaction, say, between a Higgs and a squark and another Higgs and another squark. Okay, so it has there are lots of different interactions embedded in this. From the supersymmetry point of view, we've just written down three possible cubic interactions which are gauge invariant. Now it turns out that there are many more interactions that we could have thought of. Interactions we could have thought of, and let me write a few which are consistent with all the known symmetries of this system so far. So here is one. We take a lepton and we dot it with H2. Okay. Hopefully, if I go back to my notes, I'll find that the hypercharge of this lepton doublet is -1. That makes sense. Yes, thank you. So this conserves hypercharge, and this is a doublet with a doublet, so I can dot it. And this free index I is not a problem. This is the family index, but there is no symmetry of the theory associated to this I being 1, 2, or 3, which is the electron, muon, and tau families. So I can put any constants in front, and I can have such a term. So this is one possible term that's not in that list. Here's another one. I take two lepton doublets, I dot them, and I put in an E bar K. So again, if there's some justice in the world, this should have hypercharge 0. I haven't actually checked, but whoever is busy with this hypercharge table can please keep checking for me. You see, once we get in the business of writing cubic superpotentials, then nothing really stops us writing all these terms. And you see that, for example, that in the non-supersymmetry, these are all couplings which are entirely new with respect to the standard model, because all these superfields involve known fermions and unknown scalars. But when we reduce these cubic couplings to ordinary couplings, one of the unknown scalars will appear in it. See my point? This never gives a coupling purely between known fermions. So its contribution to standard model couplings is nil. Okay. For example, what can it give? It can give a coupling between a lepton, another lepton, and a slepton. Okay, because remember the rule that for cubic couplings we pick out two fermions and one scalar, and then for the potential we pick out all scalar components. So in every case that involves leptons or squarks. So these are strictly non-standard model particles involved in these couplings, and we could have thought of them, as well as we could have thought of this, and they all respect gauge invariance, and they all respect gauge invariance. They all the invariants I want. I include hypercharge. So, in order to understand why these are not there, and more importantly, why they don't recur even if we put them to 0, they might occur as renormalization effects. There must be a discrete symmetry which puts them to 0, and turns out there is. They are all prevented by the discrete symmetry under which the L's, the E bars, the Q's, the U bars and the B bars, that is all lepton and quark superfields, go to minus themselves, but the Higgs superfield goes to plus itself. Okay? So you see that if I consider a discrete Z2 symmetry under which the lepton and quark superfield flip sign but the Higgs doesn't flip sign, then this is odd. This being cubic among quarks and leptons, these are all odd. But the ones that are allowed here are even, because this has 2 quarks and a Higgs, this has 2 leptons and a Higgs, 2 quarks and a Higgs, 2 Higgs. All of these are allowed.
Sorry, and the reason why disallow these couplings is to keep the model simple?
Yeah, so there are many different reasons to disallow. One of them, of course, is that you can quite quickly see that this will lead to rapid proton decay, because this D squark, down squark will mediate. For example, if I take one of this and one of this, then I can get 3 quarks to turn into an electron via exchange of this D. So proton decay is one reason. Simplicity is, of course, an important reason already, but this whole bunch of these possible interactions will have problematic consequences for phenomena. So good. So there's a discrete symmetry now. Yeah.
What is this? I mean, what does this symmetry mean?
Yeah, so in general you don't have to say what it means, as long as there's a symmetry that's respected by the Lagrangian and not by the terms I don't want, they'll never come back into the theory under renormalization, right? Because I take that Lagrangian, I regularize, I compute loop diagrams, whatever I like, and I'll never generate those terms because they violate a given discrete symmetry. Okay. Now it turns out this symmetry has rather profound consequences, and it turns out to be called R parity. And it is extremely important, but in order to explain why this symmetry is R parity, I need to explain R symmetry in more detail, which I will do next time. Okay. Again, R symmetry is part of a standard supersymmetry course long before we reach the MSSM, but I wanted to bypass it until we needed it, and here is where we need it for the first time. Okay. So with that, I will stop here, take a question or two if there are any, and then we'll continue next time. I think you can actually